It's very useful for many applications because it contains all the information, and it's indeed used widely for hardware, software validation, including my experience, single non-information essentially in the industry, because kind of the complex apply them to the solve regularly. And now there is this problem that satellite preprocessing, which I've presented, compatible with incremental solving, but there are some later works which are compatible. So we had a paper time ago, and then there is a paper by Kadika. Now, another useful feature in the API is unsatisfiable core functions. So if we have this incremental API, and if the formula is satisfied, then we are done. But what happens if the unsatisfied? In many usages, you would like to know part which of the assumptions are required for the unsatisfiability proof. And there is an API for that in Miniset. And the algorithm works as follows. If the conflict occurred at decision level 0, which means before assumptions are assigned, then the conflict is global. It does not depend on. Otherwise, an assumption must have been flipped. Right? So the formula, the solver can learn that the formula is unsat by either having a conflict at the global decision level, or remember that the solver works by assigning assumptions as decision literal. So assign an assumption, you run BCP. Assign another one, run BCP, etc. Only after all the assumptions are assigned and propagated, you pick your decision variables. So one way, so the algorithm can finish when you find a satisfying assignment, but other ways are first, you could have a conflict at global decision level, and second, an assumption could have been flipped. Right? If assumption is flipped, then the formula is unsatisfied. So what the algorithm does in order to discover which assumptions are responsible for the is going over the trail backwards and mark all the decision variables which are assumptions which you reach, and only those variables are responsible for it. So let me show you the algorithm as it appears in Miniset actual code. So on the input, the algorithm called analyze final, the function gets the flip assumption and the out conflict, which is in which the algorithm is going to return a set of the assumptions in the unsatisfiable core. Okay. If we are at decision level 0, then we are done. Then the conflict does not depend on the assumptions at all. Otherwise, there is the scene array which marks variables connected to the flip assumptions. And so what this function does, it goes over the trail, which is to say all the assigned literals backwards. And now, if it reaches a decision variable, then it must be an assumption, because we are at the assumption, at the decision level of assumptions, and then we just push it to the set of the returned assumptions, because this assumption was essential for deriving the conflict. Otherwise, it's an implied variable, and then we just mark all the variables in its parent clause where it was implied as seen. And so when we reach them, we just propagate our conflict until we reach like all the decisions. And so we go over the train again, and when the trail is finished, when we have completed exploring the trail, we are done. This is the algorithm of extracting the unsatisfiable core. That's an example of a simple algorithm. That's fine. So let me provide you an example of where unsat core extraction in terms of functions can be useful. So there is this technique called proof-based abstraction refinement. So in model checking, when you want to prove a property, sometimes it's too difficult for the SAT solver. So what this technique does, it just removes or cuts off all the latches from the formula, and then the formula becomes simpler, but there is an abstraction refinement loop. So what it does, there is an abstract model without the latches, and you model check it. If it's valid, there is no bug. Otherwise, there is counterexample, because we run BCP at some unrolling depth k. If it's not spurious, if it's a real counterexample, we are done. Otherwise, we run BCP over the current model, and sorry, over the whole, like with the current counter example, but all the latches. And then we update the abstract model with the latches in the unsatisfiable core. Right? So you kind of go over, again, so you have a formula, you abstract away all the latches, cut them off, and then you want to check whether the resulting formula is satisfiable or not. If it is satisfiable, if it's unsatisfiable, you are done. If it is satisfiable, if the bug is real, you are done too. Otherwise, you take your counterexample, you apply it, but you also kind of recreate all the latches and provide them their definition as assumptions. If some of the latches are in the unset core, like some of the latches must be in the unset core because the counterexample is spurious, and you update your abstract model with the unsatisfiable core of the latches. So you return only the definitions of the latches which are part of the unset core. So this is just an example of how you can use the unsatisfiable core in practice, but there are many other applications. Okay, so now I'm switching topic, okay, to another topic. Questions? All right, so now I'm going to talk about SAT-based local search, and then about optimizations with SAT, and then we'll get back to local search. These two topics are related. So assume we have a new problem. We want to find a solution near a certain assignment. So the user gave us an assignment, and we want to find a solution nearby. I'll talk about applications later, but just consider this problem. So how can you find a solution nearby a given assignment? So we had this problem some time ago, and there is a very simple idea how you can do that. You just ensure that your polarity selection heuristic always chooses the right polarity for every variable, right? So we have an assignment, desired assignment. So we want to be near it, and we don't modify the SAT solver at all except for the polarity selection heuristic. So whenever a variable is picked, we just choose the value from the assignment near which you want to find a solution, right? The target assignment. And so first of all, note that if the assignment is actually a solution, we will find it, right? Because we always pick the right value for every variable. But even if not, the SAT solver will return to the same place. So that's why I'm calling it a local search, right? It's like a local search based on SAT, right? Not a local search like standard classical local search inside the SAT solver, which Armin will talk about tomorrow. But how do you do local search on top of a SAT solver, right? Okay, like using a SAT solver inside for finding a solution near an assignment. So our original application for this algorithm, which has kind of many applications, was bug hunting. So again, we are talking here about hardware model checking, and assume that your problem is too complicated for a single BMC to cover. So we have initial states here, and you cannot go over this maximal bound of bounded model checking. But you may have bugs somewhere out there, right? Debugs. So how could you reach them? So what we did is reaching to the perimeter of maximal BMC bound, and then running a new BMC from these points, right? From the new initial state. So, and then there is another one. You get there, and you run BMC, and you continue with this process like this until you hopefully encounter a bug. So yeah, this is an incomplete process, but in practice, it's actually very useful, right? When you do hardware model checking for bug hunting, because there are debugs, complete techniques do not work, BMC doesn't work, it's too hard. So this technique can be useful in practice, but now you need to generate diverse solutions on the boundary, right? You don't want to get to the same solution, because you want to start your exploration from diverse places, right? From different places, not ones that are nearby. And that's the application. Our application for this finding a solution nearby thing, which I've shown you. So the problem is a diverse case SAT, which is about generating a user number of diverse solutions. So again, we are using it to diversify our search for bugs. Now, how is a diverse solution defined? So essentially, set of a solution is diverse if you want to maximize the Hamming distance between all the solutions. So for example, given an empty CNF, like you want to find diverse solution, so the first solution can be any solution. Let's just assume it's comprises all zeros. And the next solution, in the next solution, we must have only ones in order to maximize the Hamming distance between them. So notice, these are not random solutions, right? Once we have the first solution, the second solution, like for a tautology, must be as far away from it as possible. Then the third solution here for a tautology can be just any solution. You can pick a random value, but then you need to balance these values in the next solution, right? So for a tautology, it would work like this. But given a CNF formula, how you can find diverse solutions? So what we did there is first we find the solution, and then we just fix the polarities. After we find the first solution, we fix the polarities to the negation of the first solution. And then the next solution will be kind of near the opposite of the current one, right? And then that's how we operate. So that's the way to generate diverse solutions by being able, so the engine here, the key ability here is to be able to find the solution nearby a target assignment, right? So the target assignment in this case is just a flip. Like if you need two solutions, you just flip the actual solution you found the first time, and that's your target assignment. And you continue like this. So that was our original application for finding a neighbor solution. Questions about this idea? If not, then I'm going now to switch, talk about how you do optimization with the SAT solver. And then we will get back to the topic of this SAT-based local search. So let's consider the following problem. In plain SAT, you have only your formula to solve, but let's assume there is also a pseudo-Boolean objective function which you want to minimize or maximize. Like, what is a pseudo-Boolean function? Well, it's in its most basic form is just a mapping from every full assignment to a real number. Okay, so we have an example here, right here in this table. So we have a formula f. It has 3 models, but now, like this, a standard SAT solver would have found any of these models that would be fine. But here we want to minimize the value of the solution. So out of these 3 models, we want to choose the one with the minimal value of psi, which is M1. Right? So this is optimization in SAT in the most basic form, the basic API. So, but how can you solve this problem in practice? How can you define it or express it in practice, right? You cannot like express it with such a table on real-world instances, of course. Now, what happens? So this is the best model. What happens in practice? It depends on your target function. So if it is linear, it's linear pseudo-Boolean functions like 2 times t2 plus 5 times t1 plus 7 times t0. If it's a linear function, there is this maxed field, which is a well-established field with plenty of solvers and applications, and there are also maxed evaluations since 2006. Now, if it's not linear, there's only few words, but we are doing it at Intel. But I'm not going to talk about nonlinear part. I'll talk about maxed today. So what maxed is about, it's about optimizing a linear pseudo-Boolean function given a SAT formula. So on the input, you have a set of hard clauses which you want to satisfy. And also there is the optimization target, which is just a bit vector. And every target bit is a literal associated with an integer weight. And what you want to do is you want to find the model which minimizes the weight of the satisfied target bits, which is a linear function. And I'll talk today about unweighted maxeds, in which the weights are 1, but of course there are also algorithms for weighted maxeds. So for example, we have a formula H, and we have this optimization target T, consisting of 2 literals A and B. And H has 3 models. But for unweighted, maxed M1 and M2 are optimal because their value is 1. The value is defined here only over the target bit. So it doesn't matter. The value of C in this case doesn't matter. And the value of M3 is 2. So maxed would return M1 or M2. Now, maxed algorithms can be categorized into 2 categories, like exact algorithms or anytime algorithms. Now, let me remind you that anytime algorithms are expected to yield better and better solutions as the time goes by. And as I said, there are two categories of maxed solvers. Exact solvers are guaranteed to return the optimal solution. So no intermediate solutions are required. But in anytime algorithms do not guarantee to find the optimal solution, although some solvers do, some algorithms do. But improved solutions are output frequently. Now, for industrial usage, we are using only anytime algorithm because my worst nightmare is getting stuck. Like if there is a real problem and you run an exact solve, which is not anytime, if the problem is too difficult, then you don't return to the user any solution. It's really bad. So it's always better to return some kind of an approximation. That's why like I'm focused on anytime maxed solving. Now, how does it work? So normally anytime maxed solvers, they do local search, classical local search-based preprocessing, and then they apply SAT, a SAT-based algorithm. So next, I'm going to show you the core SAT-based algorithm, which is linear search SAT and SAT, LSU. It was invented in 2010. So this is just linear search. So what you do, first, you have a CNF formula F, like an incremental SAT solver instance F. And so first, you find your first approximation independently of the target function. So if you have a model, right, your first approximation, you just block all the models of the weight of the model you just found or higher, and you go to the next iteration. And if it is unsat, it means you can return the last model you found, and that's an optimal model essentially. So this algorithm is applied in leading anytime maxed solvers, but these days as the last fallback option in many cases. So let me show you how it works graphically. So assume we have a formula which has this solution, right? So the solutions are shown here. So every green circle is a potential solution, but we want to find this one, right? 49, the solution with the minimal cost. So what it does, first it runs a SAT solver with all the clauses, and the SAT solver could find any solution, right? For example, this one with the cost of 90. And then what algorithm does is blocking, so it saves the solution, but then it blocks this solution and all the solutions which are worse off, and it goes to the next iteration. Then it could find, for example, this model of weight is weight 54, and again, it stashes it and then goes to blocks all the models, this model and all the models which are worse, and goes on to the next iteration, and then it finds the next model and blocks it. And finally, it will find the optimal model. Once it is blocked, then there are no solutions anymore. So it goes to this case and returns just the last recorded model. Okay, so this is linear search, which starts with a satisfiable solution. Now, I wanted to give you an idea how encodings for blocking solutions work. Just I give one example, how you block solutions for unweighted algorithm. So how do you do it? You need to support cardinality constraints for unweighted max cardinality constraints of the form of this form, right? So you have your target bits, and you want to ensure their sum is not higher than some bound B. That's how LSU works, right? For weighted maxed, you would need the pseudo-Boolean constraints with coefficients. And I'm going to show you the totalizer encoding for encoding cardinality constraints for unweighted maxed. That is very useful encoding used by state-of-the-art maxed solvers. So essentially what it does, it builds a binary tree, an adder, but based on unary encoding. So recall that in unary encoding, in order to represent a number, you just, for example, to represent number 3, you have 3 ones and then a 0. So then you want to represent number m, you have n ones and then a 0. So I'll show the complexity of the encoding. So the complexity is actually quadratic in a number of clauses, but if you have a good upper bound, then it really goes down, which is very useful for LSU, because there you already start with some kind of a bound and you want to tighten it. There's also this useful feature of R consistency, which is actually appears in every practical encoding. So if B variables are assigned to 1, you must, so the rest of the target variables must be assigned 0. And this is forced by unit propagation. And if B plus 1 variables are assigned to 1, there is a conflict, right? And so we should be able to identify it. Like, so the totalizer guarantees that this is identified by unit propagation. And then another very useful feature is that tightening the upper bound is really, really easy and you know, empirically efficient. So let me show you how it works. So assume we want to build a totalizer for this constraint. So we want to build an adder at this point, and then I'll show you how you can manipulate the upper bound, which is required for LSU. So to build an adder, you just build a binary tree. So you have all these bits at the initial level, and then you create sums of these bits at the second level, like 2 bits, right? Because you want to count. And then you have 4 bits, and then you sum it up to 8 bits. So let me give you an example of how it would work for some concrete assignment to the variables. So we want to count how many variables are assigned 1 here. So the answer should be 4. What we do, we just propagate the sum upwards in the totalizer. So for example, here we have 1 bit, which is on, and here in the sum, it's also 1 bit. So this is 1 in unary encoding. Here we have both bits which are 1, and this is 2 in unary encoding, etc. So we continue this process, and eventually we have this result as expected and as required. Now we need to translate how do we represent it in clauses, right? That's what we want to do when we want to encode the totalizer into SAT. So it goes as follows. For every node in the totalizer, we create essentially 2 clauses. Sorry, a quadratic number of clauses in the number of bits, but for every combination, there are 2 clauses. So the first clause, so we go over all the bits of N1 and all the bits of N2, and assume our current bits are P in N1 and Q are in N2. So we add 2 clauses. The first clause, what it says is that, for example, if bit number 2 is 1 and bit number 3 is 1, then P plus Q is 1, right? So if we have 2 and 3, then we must ensure that the result is 5 or greater than 5. That's what it does. And the next clause ensures that if bit number P plus 1 is 0 and Q plus 1 is 0, then the sum does not go beyond a certain value, right? So if it's 2 and 3, then the sum must be lower than 5. So you can go over, again, you go over all the bits in the input nodes and create these 2 clauses. And that's it, essentially, for creating a totalizer encoding. But you need to go over, of course, all the nodes, too. And the complexity is quadratic in the number of clauses is quadratic, and the number of variables is n log n. Because you have log n levels in your tree. But when there is an upper bound, this is things get simpler, because if you have, for example, upper bound of 3, it is sufficient to just have 4 bits, at most 4 bits in every node where the most significant bit is 0, right? And then you just bind your result. Your result cannot be greater than 3. And this is very useful, and it helps empirically if you have a tight upper bound originally, right? So, for example, in LSU, it would really help to find a good tight upper bound at the beginning. And there are some heuristics for that, which I will show you. Yeah, so the complexity goes down if you have an upper bound. And then if you want to tighten the upper bound, that is really simple. If you want to go from 3 to 1, all you need to do is to assert the unit clause not O2, right, and not O1. So you just need to make sure that these bits O2 and O1 are 0, and that's it. You don't need to re-encode To create another encoding, you just need to add 2 unit clauses. And this is very helpful, again, in the context of linear search, SAT and SAT, because all you need to do there is tighten the upper bound. And you have the same encoding, the same clauses, all the heuristics operate. So this is quite useful. Okay, questions about the totalizer? Yeah, this is an example encoding, but again, it is applied by state-of-the-art anytime maxed solver because of the useful features I've described. Now, still in LSU, the convergence is often too slow because the first model might be too far away and that you don't have a tighter upper bound. And then finding the next best model can be slow too, because in the end, the cardinality constraints are heavy, can be heavy, right? The totalizer. And also the pseudo-Boolean constraints for the weighted case. So I'm now getting back to SAT-based local search. So what we found is that it's manipulating the polarity is really useful in this context. So there is this torque or target optimal rest conservative polarity selection, which is useful in the context of anytime maxed solving. So the idea is to modify only the polarity selection of the SAT solve. So we don't touch anything else. So it's still efficient. But in this context of finding the optimal solution, what we do is the following. So for a non-target variable, any variable which is not part of the optimization goal, we just pick its value in the last best model. So that's the conservative part. So we want the assignment, the next solution, to be near the previous best one. So in the local context, and it actually works quite well, but for the target bits, we want it to be as close to the optimal solution as possible. So we set the polarity to zeros. So again, this is done underneath, like the SAT solver is running, and we modify the polarity selection and the polarity selection only to keep the process efficient. This is, again, quite a useful technique in practice. And finally, to complete this topic of SAT-based local search, I'm going to show you another algorithm, which is called PoloSAT, which can be invoked instead of SAT as an oracle, right, inside MaxSAT. So this is kind of another step of local search. I'll show it to you on an example of MaxSAT. So assume you have a solution found by MaxSAT. What this algorithm does is it records all the solutions found so far, and then it tries to flip a bit. For each SAT invocation in a loop, it tries to flip a bit which has never been assigned 0. It tries to force it to be 0. And so again, find solutions nearby. So this is really implementation of local search using a SAT solver as an oracle. So you run this query of trying to turn a bit into a bad bit, but only for a limited number of conflicts, because otherwise it might get stuck. And in this way, you run kind of a quick local search loops. And this process, in practice, it helps you to find improving solutions quicker, like anytime improving solutions quicker. And there is also, so the algorithm also always applies this polarity selection torque. So this is a default in anytime maxed solvers today, but it can also be applied to optimize any pseudo-Boolean function, not only linear functions. So we use it at Intel for optimization problems. And recently there was a paper which shows it to boost pseudo-Boolean optimization. So now I'm done with the second part of my talk. So essentially what I presented there is the paradigm of incremental SAT solving, which is very useful in practice. SAT-based local search, some example encodings, and some applications like bounded model checking, abstraction refinement, and bug hunting and anytime maxed. Right? So we are now going into the last part of my talk. So we are going to follow the SAT competition winners after minisat. And if we have some time left, there will also be a discussion about incremental SAT solving. Okay, so again, this is the picture of SAT competition winners. So we stopped here at minisat last time. Now I'm going to talk about solvers derived from minisat because it's like simpler to discuss them, because one is based on on the previous one. So, and then I can kind of talk to you about the techniques easily. So the next
Alex,
source I keep
yeah. Curious that RSAT thing. Yeah, does it use any of these techniques that you talked about, or it's like knowledge compilation? Because
RSAT, it uses, I think it uses all the techniques like which existed in Minisat, but only, so I'm actually going to talk about it now.
Okay, you're going to talk.
Yeah. So, yeah. So it uses all the techniques that were in Minisat, but its like main innovation was in polarity selection. So they came up with this idea of always choosing the latest polarity. It's called phase saving. Right? So now we are back to standard SAT solving. So no optimization anymore. We don't have a target optimization function. What we do to improve classical SAT solving for this SAT decision problem. So and so far, till RSAT in Minisat, Minisat always picks zeros as a polarity for every chosen variable, and I think it also did some randomization from time to time. But in RSAT, they noticed that it makes sense to always pick the latest polarity for every chosen variable. Now, again, it brings us back to this locality principle in SAT solver. So you want to work on already explored subspace and to glean some information, to derive useful clauses from that space. So again, it's in the spirit of locality. And it works well in practice. So let me just give you an quick example. So for example, we have that formula and we are here. At this point, we want to choose between C and not C. But since the latest polarity of C was positive, right, we just choose C. But if the formula were different, if we had like C here in the formula and not C as a decision here, then we would choose not C. So it goes with the latest polarity. It's as simple as that. Now, as I said, again, we are talking about the locality principle, and this simple heuristic used to be the state-of-the-art heuristic till 2020, and then things got really complicated and interesting, and Armin will talk about phase polarity selection tomorrow. Okay, so this is RSAT. Now I'm going to talk about crypto-minisat. So it was introduced in that paper, 2009, and the motivation was to kind of to provide better modeling or separate modeling for XOR clauses. Because XOR clauses are notoriously difficult. Now, why is that? They are difficult for SAT, intrinsically difficult for SAT. Well, this is because pruning doesn't work well for XOR gates. Okay, so if you have an AND gate, right, if A is 0, independently of the value of B, Q must be 0. Right? There are opportunities for pruning. And if Q is 1, there is output is 1, then both A and B must be 1. So if you have one value, one literal sign a certain way, you can propagate this information in order to prune your source space, but this is not the case for XOR clauses, right? You need to have 2 out of 3 variables assigned, and only then you can propagate. That's why they're difficult. Right? XOR and equality too. Yeah. So crypto-minisat is still under active development, and there is a link here. Now, what they did in crypto-minisat, like back then in 2010, I'm not talking now about the modern version. So there was the component of handling XOR clauses, which I'm not going to talk about. For polarity selection, it used phase saving and occasional random flipping. And there was a separate heuristic for cryptographical versus industrial instances. And then there were 3 techniques, which I'm going to present next. Like some of them I'm going to present quite briefly. On-the-fly subsumption, fair-literal probing, and hyperbinary resolution. So now I'm going to describe the process of conflict analysis, answering a question, from the first part of the talk, how conflict analysis is done in practice, right? Not using this implication graph just for us human to understand, but what is going on in practice. So this is essentially done by resolution. Now let me show you this process and conflict analysis using resolution and compare it to resolution to also to the implication graph. So assume on an example, assuming we have the formula on the left-hand side, we just go ahead with CDCL exploration. We assign A1, B2, then we have a propagation of C at level 2. But now it is convenient to specify the parent clause as part of the decision tree. So every implied literal also has a parent clause, a clause where it is implied. So in case of C, it's implied in C1 because B is 1. So we just write it down, the parent clause. Then we have another implication. D is implied at level 2 in clause C2. And then we have a conflict because E is implied both in C4. So not E is implied rather in C4 and E is implied in C3. So we have this conflict. Now, this is the implication graph. So now the process of deriving a conflict clause, we can think of it as the process again of having this cut moving from the right-hand side of the implication graph toward the left-hand side. But you can also do it by resolving upwards from the conflict. Let me show you how it is done. So here we have a conflict, which means that we have a conflicting literal, and which must appear in different polarities in the parent clause, right, E, and in the conflicting clause, not E. So we just resolve over E. We get a clause not A or not D by resolution, but it also corresponds to this cut in the implication graph, the closest cut, right, to the conflict. So and then we go upwards in the tree and leftwards in the implication graph. So we resolve over D here, and we get this new clause not A or not C, and this is like, and we go leftwards in the implication graph to get the same clause. So this is the same clause, right, which corresponds to that cut, etc. So eventually we get to this clause not A or not B, both on the decision tree and also in the implication graph. And now we can continue with CDCL. We can flip B in this case. Yes.
A1 to E2 edge doesn't occur analogously in the right side.
Say it again.
That top edge, A1 to E, the top one to the rightmost one. A at 1 to E2. On the implication graph.
On the implication graph, the topmost edge, yeah. So this one.
Yeah. It doesn't occur in a similar fashion over there. In the first cut, 3 edges are cut, right? But in the resolution side, only 2 are showing up.
Oh, there is this C4 clause, right? It's part of the C4 clause, so it's like here. It's part of the C4 clause, so you go over it. So you kind of cross it several times. You cross it in the implication graph. You cross it several times. Each time you cross it, there is a resolution. So for the right cut, there is the resolution. I'm too far away from the computer. The resolution is here, and for the next cut, this one, the resolution is here, and then for the last cut, the resolution is up here. Kind of.
Okay. The C4 cover both the edges. Okay. Got it.
Other questions? Okay. Yeah. So another thing, what happens if the variable is not in the implication graph? So it's not in the decision tree either, right? So for example, assume there were a clause C0, which does not impact the conflict. And so you would have like another implication of F here, which again is not part of the conflict, so we don't need to resolve over F, right? But what we do, we just copy the clause, the last clause, right, and move up. We just skip over. If there is a variable which is not part, which we visit, we want to backtrack over in the decision tree, and we visit it in it's not part of the current result, we just skip it and copy the result upwards. Okay, and this variable is not part of the implication graph. So this is just to complete the picture. Okay, so this is conflict analysis resolution. And once we understand that conflict analysis is actually done by resolution, there are some techniques which I can present you, useful techniques. So first one is on-the-fly subsumption. It can happen that an intermediate resolvent subsumes a clause. So let me show you. So here, for example, this intermediate resolvent, not A or not D, subsumes C4, right? So what you can do is just remove, like substitute C4 by this intermediate resolvent. The same goes with the next one because it subsumes C2, right? So again, you do the simplification. So you have kind of subsumption for free on the fly. Okay. So this is this technique. But here there is no subsumption. Another technique is fed literal probing, which is essentially an in-processing technique. So it's not carried out during the search, like satellite byte at the beginning, or is part of in-processing, can be done at some point after a restart. So the idea is as follows. So I'm going over only the generic idea, not like details of the heuristics. So for every variable v, you assign it and you run BCP. So it is done at the beginning of the search or after a restart where all the variables are unassigned. So if you run a variable v, if you assign variable v and run BCP, there could be a contradiction. If there is contradiction right away, it means that not v always holds, right? V cannot be true under this formula. And so you add the unique clause not v and continue to the next loop iteration. If not, then you do the same thing with not v, with the negation of the variable. And again, if there is a conflict, you can add the unique clause v and continue. And then another thing which you can do is record all the literals which are implied by both v and not v. And if there is such a literal, you can learn it. It always holds. If a literal is implied by both v and not v for any v, it always holds, whatever you do. Okay? You can easily like derive this fact by resolution. V implies L means amount to the clause not V or L, and not V implies L is the clause V or L, right? So if you resolve these both clauses, you get L. So this is fed literal probing. There are many heuristics how to make this process efficient, because if you just run over every variable, it will, I don't know, it will slow down your solver, it won't work, but you need to do it cleverly for some subset of variables, etc. I won't present you the details here. Questions?
Maybe you'd want to try this with literals that appear in small clauses or something?
Yeah,
Okay.
yeah, and also literals with high score, because we remember we keep these visit scores. So yeah, that's in practice, that's what people are trying to do.
Thank you.
Because in binary clauses, like you said. Right? Yeah, so it's just pointers to the papers. Another thing which I wanted to mention, another technique rather, is hyperbinary resolution. So here we have a long clause, L1 or L2 or L3, etc. V, and then and Ln, right? Ln is part of the first clause. And then we have binary clauses, right? Which essentially what they say is L1 implies L, L2 implies L, etc. And so we can learn the clause Ln or L out of, if we encounter this, like we can resolve the long clause with every other binary clause. Right? If we resolve the long clause with not L or L, we just substitute L1 by L. And then we resolve it with the next clause and we substitute L2 by L. So eventually, if there's, there is a problem here with the font. So here, what is written here is not Ln minus 1 or L. So we don't have this binary clause for the last literal Ln. So Ln persists, but all the other literals are replaced by L. Okay? So that's the technique. So you can do it by using some binary implication graph. And this actually sums up what cryptominiset does. So we now go to the next solver, which is glucose. Any questions so far? No? Okay. So we go to glucose, which is kind of a famous solver too. It was derived from Minisat and still used in many incremental applications. It introduced the literal blocking distance, LBD, for measuring close quality. And then the set of heuristical strategies of glucose are based on LBD measure. And there are some changes in VSIT's implementation and binary resolution during conflict analysis, which I'm going to mention too. So the authors of glucose asked this question: what makes a conflict clause a good one? This is a very important question because, again, like we have these filtering techniques, we want to like delete some clauses, and so we want to stay with good clauses. And they came up with this idea of LBD, which is a literal block distance, which is the number of decisions level in the clause. You want to have as few decision levels in the clause as possible, because, well, heuristically, these variables were when these variables are propagated together, they're related and likely to be propagated together again. So again, if the variables belong to the same decision level, that means that they were propagated together. They have something to do with each other, right? They're related. So this is the idea. So again, this locality principle want to focus on the relevant local data and learn strong clauses from local context. So whenever a new learn clause is derived, LBD is not kept for initial clauses, and because we don't delete them. But whenever a new learn clause is derived, we associate it with this LBD score. We also update LBD scores whenever a clause is visited during conflict analysis to make it up to date. And it's widely used by model solvents. So in glucose, there was LBD-based clause deletion. So it deleted half of the clauses based on the LBD score. And there are some magical constants here again. But the idea is that you want to keep clauses with low LBD score and remove clauses with high LBD score. That's the idea, right? And so you always want to keep clauses with LBD equal to 2. And there are some optimizations here, but I'm going to skip them, right? Just remember the main idea. LBD score is low, you want the clause to remain. Right? And the restart strategy in glucose is also based on LBD. So the idea is when the LBD of the latest clauses is high, you want to stop and restart, right? And so it keeps the average of LBD score, and if it's higher than usual, it restarts. But then the original technique was found to be too aggressive because you may be near the solution and then you restart because the LBD scores are bad. So it's not good for satisfiable instances, and so on. There is this technique of postponing restarts when the number of assigned iterations suddenly grows, so that you would stay in the same neighborhood for satisfiable instances. So glucose implemented like a combination of this technique. LBD is mostly good for unsatisfiable instances or unsatisfiable subspaces, and this the idea of postponing restarts when the number of assigned iterations is high is good for satisfiable instances. I'm not going like to describe the details of magical constants. Now, the VSIDs in glucose is kind of more aggressive. It updates, or like in end, it's also gradual. So at the beginning, it upgrades the scores more aggressively. It multiplies them by a higher factor, and only after some kind of like a considerable number of conflicts goes by, it works similar to Minisat. So first, it gives kind of a boost of scores at the beginning, and then it gradually makes the search more stable. So that's the idea. Okay. Now I'm going to introduce another technique, which is there in glucose and also in modern solvers, which is binary resolution during conflict analysis. So now we resolve with satisfied binary clauses, which you haven't done so far. Let me show you an example here. So we have these clauses, like this decision tree and implication graph with this new clause learned. Now, we cannot apply minimization here, because minimization, like if you want to remove C, we would introduce A. If you wanted to remove B, we would introduce A again. So we cannot apply conflict clause minimization. We cannot resolve with parent clauses here. But what we can do is resolve with this binary clause B or not C, which is satisfied, to derive like to simplify the conflict clause. Right? So you can pick a chain of binary clauses and do it. This is again quite a useful technique because it's kind of cheap, because you only go over the binary clauses and it enhances or simplifies the newly run clauses. So yeah, there is a heuristic of binary resolution. Let me skip this slide. Okay, so this sums up glucose. For preprocessing, again, it does satellite, so it hasn't changed. For decision strategy, it does e-visits, which is kind of updated with a different score management scheme. So at the beginning, the scores are upgraded more aggressively, and then it slows down. And for conflict analysis, it does minimize first UIP with binary resolution, and it has LBD-based restarts and close deletion. So I think the main notion, like the main novelty here is LBD, and also binary resolution is quite useful. Questions? Okay.
Yeah. So I guess in this loop, the while loop, pre-processing in between, which is like
in glucose, no, it's just pre-processing, it's not in processing.
So glucose has no in processing at all.
In processing, I think it was part of Linglin. But what solver source implemented?
No, the original glucose doesn't have, but like since 2013, the others, like Maple versions of it, they do
Yes,
have.
This is the original one. Yeah, okay. So now we are going to this line of solvers which derive from Minisat. So we are going to go over them, and because again it's easy to, for pedagogical purposes, it's like makes sense to introduce this technique gradually by going over this chain. So now I'm going to talk about Minisat, which is a solver. So it hasn't won a single competition, but then the solvers based on it won a series of competitions, like right between 2016 2019. So in Co-Minisat PS, that was the name, not just Co-Minisat. The main idea was that there is a difference, there should be a difference between handling satisfiable and unsatisfiable instances. Because for unsatisfiable instances, a proof is required, so you need strong conflict clauses, right? And then all these ideas of refocusing your search like make sense and they work efficiently. So you want aggressive restart strategy and visit score update for unsatisfiable instances. Whereas for satisfiable instances, so in principle, you should be, if you make a right guess, you can just complete it without any search at all. So it makes sense to do things differently. And so you want your research track to be slow, and also your visits update to be score to be slow. But again, it's not exactly true, because even for satisfiable instances, you can go into unsatisfiable subspaces, and there you would want to kind of apply these ideas from this unsatisfiable part. But still, you want to give a chance for the solver to complete solving your satisfiable instance. So the idea there was to have several stages, like to run this, so to have a SAT stage and unsat stage, and also there was a change in the closed deletion scheme. So, but for the SAT and unsat stages, it worked as follows. So at the beginning, there is a warm-up stage of unsat stage for a certain number of conflicts. And then it went from SAT to answer stages, right? Intermittently. So for the SAT stage, there were no restarts and a very slow visit score increment. For the unsat stage, there was a glucose LBD-based restarts, which are very aggressive, and an aggressive update of visit scores. That was the idea. And this is a very useful idea. And again, tomorrow Armin is going to talk about like modifications to it, but this is kind of the basic idea. SAT and SAT stages. And another thing they introduced was a 3-tiered scheme.
Alex, yeah, could we go to the previous? So I guess if you have more than C conflicts, so you start in the unsat stage, right? And if you're not able to prove unsat within 10,000 conflicts, then go to
into a loop
this.
in which you have both SAT and unsat stage. Even though the first stage is called unsat stage, you can also find a solution somehow, right? So if you are unable to complete the process during the initial conflicts, you go into a loop in which you apply a SAT stage for C conflicts, an unsat stage for 2 times C conflicts, and then you also update C. So we will always have SAT stage and unsat stage, where the unsat stage is longer. Again, there are some magical constants here which cannot be explained, but that's how.
But is there a rationale for starting with the unsat stage, or
just empirical?
empirical?
Like, yeah. So yeah, this is the 3-tiered close management. So for closed addition, you have 3 tiers. You have clauses in the core tier you want to keep forever with a low LBD score. And so it's lower than 3, but it can go up to 5 under some circumstances. And they're tier 2, so from which you still don't delete clauses, but you relegate them to local, to the 3rd tier. Again, it's based on LBD. And then there is the final tier. So if you remove clauses from that tier, they're actually deleted, but they can also be promoted to tier 2. So if at creation, let's say if at creation the clause had an LBD score of 10, but then if you visit it again, you updated its LBD score to 6, for example, then it will move up. It will be promoted. So you can relegate and promote clauses here. So yeah, again, this is kind of empirical data. It works well in practice. Now we go to this solver. No, that's correct. Yeah, so in this solver, whose name is, you cannot see it here, there was a new decision heuristic called LRB, and the idea was to boost variables which might impact during the latest assignment term. Again, the idea here is to focus on locality. So let's say that a variable V was picked, and then there have been many conflicts here, and we keep track. So we have the number of conflicts, but we have also the number of conflicts in which the score of V was updated. So we want V to participate in as many conflicts as possible during this assignment term. So we have this function, right? So we have this number of conflicts in which V score was updated. We want it to be as high as possible, and we have the number of conflicts during the latest assignment term, which is the age. And so this is LR is our measure, and we want it to be as high as possible, right? Yeah. So there is like an algorithm which does it, which I'm going to skip with all the details. Just remember the idea. So the general idea was to consider the latest assignment term of a variable. And now there was a different way to combine between SAT and unsat stages. So again, there is an unsat stage for warm-up, but then there is also a SAT stage till certain timeout. Okay, unsat stage and SAT stage, and then there is an unsat stage forever. and these are the so, and for the SAT stage is applied the so-called Luby restart strategy, which is represented by the graph here. And LRB decision heuristic only for the SAT stage, and for that SAT stage, it was glucose restart strategy, LBD based, and glucose EV-sits. So now we are going to the next solver. Here again, there was a change in decision heuristic and another in-processing technique. So the distant decision heuristic was applied only for the first 50,000 complex, I think. So it was based on the observation that at the beginning, the variable score are inaccurate because it's based on only few conflicts, so the solver hasn't stabilized yet. And so the idea there was to, only for the first initial stage, to have a separate priority queue, different from visits, and increment the activity of variable there depending on the longest distance between V and conflict. So you want the variables at the beginning to be as close to the conflict as possible. If the variable is close to the conflict, then we want to move it up. So that's the idea of this distance technique. Again, I'm going to skip the details. And I talk a bit now about vivification, which is an in-processing algorithm. So in processing, it occurs on the global decision level 0. So this is another idea like failed literal problem, but different. So you go over all the clauses and you want to simplify every clause. Again, this is done using some heuristics, not just globally over all the clauses, but I'll talk a bit about it later. So we go over the clauses. Let C be a clause. So we go over all the literals of C at the global decision level. We assign the negation of the literal and run BCP. But then, before that, we check. So if our current literal is already assigned 0, then we can remove the literal from C, continue to the next loop iteration. Now, why is that? Because remember, we assigned the literals before CI to 0, and we can easily show that not CI is implied by the previous. So not CI is implied by the previous assignments, and so we have this clause representing this implication, and we just resolve it with the original clause. And this is a proof that we can remove CI from the clause if it's assigned 0 during the process. And then if CI is assigned 1, it actually means that we have this clause. We have proven that this clause holds. Like we only have the literals from C1 to CI. And so this clause subsumes C. We can replace C by this clause. Again, this is because CI is implied by the negations of all the preceding literals. It amounts to this clause, and this clause subsumes C. And so this process is called vivification. And there are, of course, questions how to do it efficiently. And so in Maple LCMD, it's done only over learned clauses, and it's done all after clause database reduction, only for clauses which haven't been vivified, and with small LBD, and then it goes in the default order of literals in C, because the watch list scheme shuffles the literals, and it turns out to be efficient. So that's vivification. Now we are going to this solver. So now I'm going back to chronological versus non-chronological backtracking question, which we have discussed earlier in the first part of this talk. So let me remind you this conflict analysis algorithm, right? With which I think I concluded the first part of the talk. So there is this backtracking stage before conflict analysis. Then the solver learn an asserting clause, which is the first AP clause for grasp and chaff and other solvers too, and optional other clauses. And then there is the step of backtracking to any level. So if the current level is delta, we can back through any level between delta -1 to beta, which is the second highest level, because our goal here, remember, we need only one literal of the conflict clause to be unassigned, because then we want to flip it. So we learn conflict clause. We have one literal of the latest decision level there because that's by construction, the first P clause always has only one literal of the latest decision level. So we can backtrack to any level in between beta and delta minus 1, where graph always backtracks to delta minus 1, and this is chronological backtracking into this terminology, and CHAP always backtracks to beta. Now, the CHAP's algorithm, which does non-chronological backtracking, used to be the default one for a long period of time, until 2018. Then, this solver, so this was our work, which was published SAT 6 years ago, in which we investigated chronological backtracking. And I actually found that doing non-chronological backtracking all the time is not that efficient. So it's better to combine them. So what we had is a heuristic which chooses between chronological and non-chronological backtracking. So for the warm-up first conflicts, we used only NCB. And then after that amount of conflicts, the choice between CB or NCB depended on how far the backtrack level is from the conflict level. So if it's too far away, we wanted to backtrack chronologically, right? Because we don't want to all the time to go like, if we're near a model, then we want to stay there, right? We don't want to backtrack in an uncontrollable manner all the time. So I can perhaps tell you how we stumbled upon this idea. So I had so a user reported me that there is an instance, a huge instance which had like 1 billion of clauses, which should have been easily satisfiable, but our solver just couldn't solve it. And so I started the investigation, and what I found is that it can solve it because there are unit clauses which are derived almost near the completion. So assume there are like 200 million variables, and you assign them values and propagate them. And the problem is easily satisfiable. But what happened is that when the solver got almost to the completion, to the solution, it got a new unit clause, and it just backtracked all the way up to the global decision level. And so there I thought that maybe like doing chronological backtracking would actually solve this problem, and it did. And so then we experimented like in a generic solver and found that it makes sense to combine between chronological and non-chronological backtracking also in generic SAT solving. But then the problem, so the idea of the algorithm, chronological backtracking, was very similar to GRASP's. But in GRASP, GRASP watched all the watches, all the literals all the literals in every clause. And it turned out that if you want to combine chronological backtracking with 2 watch literal scheme, it's really non-trivial, and it breaks some invariants. So let me show you an example why this is a problem. So assume we have this clause, so which at conflict time, it has 2 unassigned literals and 2 falsified literals. Now with chronological backtracking, remember, we can propagate at any level. Even though at level 30, for example, we can still propagate at level 1, right? So if we propagate at level 1 for some reason, then this clause, so we could assign the first literals during BCP, right? And which are assigned at level 1. And we don't want this clause to remain like this. Like we need to shuffle the literals here. We must ensure that after conflict analysis, after we visit these 2 literals, the 2 first literals, we shuffle the clause. We want to bring the literals which are assigned at the high decision level to the beginning of the clause. Otherwise, we have a correctness problem, right? Because assume we backtrack after the conflict analysis, we backtrack to decision level 19. This clause will not be watched anymore. Like if it stays like this, because the first 2 literals are falsified. So, and if we backtrack to level 19, the last 2 literals would be unassigned. Therefore, we wouldn't watch this clause, and we might miss a conflict. So what we need to do is to bring, so whenever we visit a clause and the clause is falsified, we need to bring the 2 highest literals, 2 literals assigned at the highest decision level, we need to bring them forward. This is essential for correctness, right? So if you have chronological backtrack and BCP, you must do it. Otherwise, you have a correctness problem. And so this is very tricky when you get to implement the ideas. And now, even if you ensure correctness, there are some useful invariants that are still violated. So one of them is lowest implication. So this situation, you see, we have a satisfied literal at level 20. But it could have been applied at level 10 in this clause, which is a better idea because you want, again, to shrink your trail. And this is not guaranteed anymore with chronological backtracking. Another thing which is not guaranteed, which relates to a question asked at the first part of the talk. So with non-chronological backtracking, you always guarantee that if you find a conflict, it is a conflict at the latest, at the highest decision level. Sorry, at the lowest possible decision level. But with chronological backtracking, you can find different conflict clauses which correspond to different decision levels during one conflict, which is also a problem. You want to start, essentially want to start with the conflict derived at the lowest possible decision level. Otherwise, you would encounter this conflict over and over again during conflict analysis. So this is still violated. Now, I have this new SAT solver Intel SAT, in which I have a new formally proven BCP algorithm with a possible solution to satisfy these two invariants. And so I gave this talk or previous version of this talk at Flock 2022. And what I wrote there is that I am expecting new formal frameworks and some empirical insights, because you can do a lot of things here. And there is going to be a talk at this SAT, Crazy implication in chronological backtracking, which explores some different things which you can do, like by Robin Putler and the colleagues later in this SAT conference. All right, so we have only 10 minutes left. So what I'm going to do now, I think I'm going to skip some slides here. And I'd like to talk a bit about incremental SAT solving. So what happened in incremental SAT solving since Minister? So far we have mostly discussed in the third part, we have discussed non-incremental solving techniques, okay? But are the solvers still incremental? And is there anything you can do to specifically improve incremental SAT solving, right? Because this is an important question, because as I've mentioned, like at least industrial applications, most of them, if not all of them, are based on incremental solving. So glucose is an incremental solver, and it has a dedicated features. So it ignores assumptions in LBD calculations. Crypto-mini-SAT is incremental. Now, Maple-based SAT competition winners, many of them are not incremental, but there is a version which is MERGE-SAT. There were 2 incremental tracks in SAT competitions. The last one won by Crypto-mini-SAT like 4 years ago. Now, KISS-SAT is not incremental, but Cadical is. And there is the latest paper about Cadical published like several weeks ago, I think, at CAP conference, in which Cadical, the new version of Cadical is shown to outperform Crypto-mini-SAT on SAT competition instances from the latest SAT competition and some other instances. So in that sense, there is a progress. Now, I'd like to talk a bit about my own solver. So I wrote a solver which Intel, I had to go through a very complicated bureaucratic process, but eventually I was able to publish it. So it's an open source solver. And it's optimized towards incremental applications with multi-satisfiable queries. So why I did it this way? Because I had so I still have applications in optimization, and there I needed to improve the performance of these applications. And in the paper, the applications anytime unweighted maxed, which is kind of similar to our industrial applications of placement, routing, and scheduling, like at least conceptually. One idea there, my solve, which I wanted to mention, is incremental lazy backtracking. So it is an optimization targeting specifically incremental SAT solving. So if there is a new incremental query, so previous solves backtrack to decision level 0. But what I did, so I'm just staying at the highest possible decision level. So for example, if there was a SAT solving under assumptions A, and there was a solution, and then there is a new set of assumptions which includes A and some other decision variables which are satisfied, you don't even need to backtrack at all. You have the same solution, right? And there is if only a subset of the assumptions, first assumption is satisfied, you just go to the high decision level, under which the most assumptions from the last query are satisfied. And this is also implemented now in the latest Cadical, this technique. And also there is chronological backtracking with reimplication, right, which guarantees lowest implication and lowest conflict. And I'm going to finish with this slide. This is kind of a philosophical question, debatable question. Is progress on SAT competition benchmarks relevant to incremental SAT solving? So there was a paper like 3 years ago at SAT conference, which says no, there was no progress since 2013. So what the authors of that paper did, they showed that glucose, the latest glucose, is on par with the leading SAT solvers at that time, maple-based solvers, on SAT-based maxset, we kind of anytime maxset, unsat-based maxset, which is exact maxset, and minimal unsatisfiable core extraction. So in the first application, there are mostly SAT queries, and the second one mostly unsat queries. And the last one, there are mixed queries, but all the queries are kind of quick and rapid. And so they claim that there is no progress because on these applications, like there is no empirical progress. And then they also showed that none of the 5 latest techniques which improved non-incremental SAT solving have a significant positive impact on incremental SAT. So there was this result. And back then, at 2021, it actually matched my own experience. There was no progress on incremental optimization problems. That's why actually this observation triggered the development of my solver, Intel SAT, right? And so one such application is placement and physical design. Now, there is this new result now in the Cadical paper that there is a progress on variety of benchmarks, but unfortunately, there are no results on those benchmarks from that 2021 paper. So we don't know if there is progress on those benchmarks. Now, my take, intuitive take, I have not run any experiments, it's that, so the answer to this question is there's progress, depends on the application. So for heavy SAT invocations like bounded model checking, any progress in non-incremental solving is relevant, and then there is incremental processing, which can be helpful. For light SAT invocations like max SAT, minimal unsat core extraction, or PDR, which is a complete model checking algorithm, I don't think that, like, most of the techniques are not relevant, but ILB, this incremental lazy backtracking, can be helpful. So it depends. I believe that it depends on the application, but of course, I have to provide more rigorous empirical evidence to back up my claims. And so we are done for today. So this is like one of the first slides in my presentation. So I still believe CSAT is an unresolved mystery. So it's really fascinating topic. But still, SAT solvers are scalable tools, and we have some intuition at least how to solve some practical problems. Maybe we barely touched the tip of the iceberg. It could be that there's some other breakthroughs and algorithms, but I try to convey you some intuition of what we know up to date. Okay, so thank you for your attention.
So thank you, Alex, for very engaging sessions. So here is a small memento for you from the organizers. And I've been asked that you should open it and see it, maybe, and show us. Or I don't know what it is. So
Let's see. I want to break it.
Okay.
Wow.
Oh, I see. Okay.
It's really cool. Elephants. Yeah, I've seen many elephants like statues on my way from to Pune, right? From Mumbai.
Right.
Like there's a Ganesh, right?
Yes, that is a god with an elephant head. I guess there is some description of the art. I think this is
Mythological white elephant who carries the Indra.
okay.
Oh,
All
thank
right.
you very much.
Thanks a lot, Alex. Oh.